Right now, at this very moment, a star is moving toward our solar system. It is not slowing down. It is not drifting aimlessly through the galaxy. It is on a trajectory that will bring it closer to our sun than any star has come in recorded history. Closer than any star is projected to come for millions of years afterward. Its name is Gliese 710. It is a dim, orange-red dwarf star, currently sitting about 64 light-years away in the constellation Serpens, and it is heading directly at us. Not approximately at us, not vaguely in our direction. The calculations have been refined multiple times, using data from some of the most precise astrometric instruments ever launched into space, and they all converge on the same conclusion. In roughly 1.3 million years, Gliese 710 will pass through the outer reaches of our solar system. It will enter the Oort cloud, that vast cold reservoir of trillions of icy bodies that surrounds the Sun at distances of up to 100,000 astronomical units. An astronomical unit is the distance from the Earth to the Sun. About 150 million kilometers. The Oort cloud extends roughly 1.5 light-years from the Sun, and Gliese 710 will come well within that boundary. The latest and most precise estimate, derived from data gathered by the European Space Agency's Gaia satellite, places the closest approach at approximately 10,360 astronomical units. That is a small number by interstellar standards. The nearest star to our Sun today, Proxima Centauri, sits at roughly 268,000 astronomical units. Gliese 710 will come more than 25 times closer. It will be, by a significant margin, the nearest stellar neighbour our solar system has had in at least the last several million years. And here is what makes this worth your attention. When a star passes through the Oort cloud, it does not pass quietly. Its gravity reaches out in every direction, tugging on the billions upon billions of comets and icy bodies that have been sitting in cold, stable orbits for billions of years. Some of those objects will be pulled outward, flung into interstellar space, lost forever. But others will be nudged inward, toward the inner solar system, toward the planets, toward Earth. A close stellar flyby is, in effect, a gravitational hand reaching into the deep freezer of the solar system and throwing its contents toward the Sun. The result is what astronomers call a comet shower, a sustained increase in the number of long-period comets entering the inner solar system, lasting potentially millions of years. And some of those comets will cross the orbit of Earth. This is not a distant, abstract concern. The geological record on Earth bears the scars of past cometary and asteroidal impacts. The most famous occurred 66 million years ago, when an object roughly 10 kilometers across struck what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater and triggering the mass extinction that ended the age of the dinosaurs. That impact released energy equivalent to roughly 10 billion Hiroshima bombs. It set the atmosphere on fire. It blocked out the sun for months. It killed approximately 75% of all species on Earth. And it was caused by a single object, smaller than many of the bodies drifting in the Oort cloud. By the end of tonight, you're going to understand exactly what Gliese 710 is, where it is, how fast it is moving, and what will happen when it arrives. You are going to learn how astronomers discovered its trajectory, how they measured its speed with extraordinary precision, and why the encounter, while not an immediate threat, raises questions about the long-term survival of life on Earth. You are going to explore the Oort cloud, a region of our solar system that no spacecraft has ever visited, and discover why it is both one of the most important and one of the most dangerous features of our cosmic neighborhood. And you are going to confront a fact that is both humbling and unsettling. In the timescale of the galaxy, close stellar encounters are not rare. They are routine. Our solar system is not a fortress. It is an open field, and the galaxy is full of passers-by. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. What follows is not speculation. It is not science fiction. It is the measured, calculated, peer-reviewed conclusion of modern astrometry and celestial mechanics. A star is coming. It will arrive. And when it does, it will reshape the outer boundary of our solar system. in ways that could echo for millions of years. The comets it dislodges will not arrive all at once. They will trickle inward over hundreds of thousands of years, a slow rain of ice and rock falling toward the warmth of the sun, crossing the orbits of the outer planets, the inner planets, and possibly Earth itself. We will not be here to see it, but the process it sets in motion is one that has shaped the history of life on this planet before and may shape it again. Now, let's begin. To understand why Gliese 710 matters, we first need to understand the space it is moving through. Not the empty static void of popular imagination, but the real space between stars, dynamic, crowded on cosmic timescales, and governed by the slow, patient choreography of gravity. Start with the Sun. Our star sits roughly 26,000 light-years from the center of the Milky Way galaxy, about halfway out along one of its spiral arms. The Milky Way contains somewhere between 100 billion and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter and about 2,000 light-years thick. The Sun, along with every other star in the disk, is orbiting the galactic center. Our orbital speed is approximately 220 kilometers per second. At that speed, it takes our Sun about 230 million years to complete one full orbit, a period sometimes called a galactic year. The Earth has existed for roughly 20 galactic years. The dinosaurs went extinct less than a third of a galactic year ago. Now here is the first critical point. The stars in the galaxy are not stationary relative to each other. They are all moving, each on its own orbit, each with its own velocity, influenced by the gravitational pull of the entire galactic mass. Most of the time, the distances between neighboring stars are enormous. The average spacing between stars in our part of the galaxy is about 4 to 5 light-years. At highway speed, say 100 kilometers per hour, it would take you approximately 50 million years to travel from one star to the next. At the speed of light itself, the journey to the nearest star takes over 4 years. But stars do not maintain the same neighbors forever. Their orbits differ slightly. Some move faster, some slower. Some have orbits that are more eccentric, carrying them above and below the galactic disk. Over millions of years, stars drift past each other, sometimes coming close, sometimes passing at great distance. The galaxy is like a vast, slow-motion crowd, with each star walking its own path, occasionally brushing shoulders with another. The stellar neighborhood of the Sun, the collection of stars within about 50 light-years, has been studied extensively. It contains roughly 2,000 known stars, ranging from brilliant blue-white main sequence stars to dim red dwarfs barely visible through the largest telescopes. The nearest, Proxima Centauri, is a tiny red dwarf at 4.24 light-years, part of the Alpha Centauri triple system. The next closest, Barnard's star, is a red dwarf at about 6 light-years, notable for its rapid motion across the sky. It has the highest proper motion of any known star, moving at about 10.3 arcseconds per year, though even at that speed, it would take about 180,000 years to move the apparent width of the Moon. Most of these nearby stars are small and dim. Red dwarfs, the most common type of star in the galaxy, are too faint to see with the naked eye even at distances of just a few light-years. Proxima Centauri, despite being the nearest star to the Sun, has an apparent magnitude of roughly 11, far below the threshold of human vision. This is relevant to the Gliese 710 story, because it means that stars can approach the solar system very closely and remain invisible to casual observation. Gliese 710 at magnitude 9.7 is similarly invisible without optical aid. The galaxy is full of unseen visitors. If the Sun were the size of a grain of sand, about 1 millimeter across, the nearest star, Proxima Centauri, would be another grain of sand, sitting approximately 27 kilometers away. The space between them would be empty. No dust, no gas, no particles you could see. Just 27 kilometers of nothing, separating two specks of sand. That is the average density of the stellar neighborhood. And Gliese 710, when it makes its closest approach, will come to within roughly the equivalent of 1 kilometer from our grain of sand. In a galaxy where stars are typically separated by tens of kilometers at this scale, 1 kilometer is extraordinarily close. Now let us look at the solar system itself, because the encounter with Gliese 710 is not about the star hitting Earth or even coming close to the planets. It is about what happens at the edges, the far, cold, forgotten edges of our sun's gravitational domain. The solar system has a structure that most people are familiar with, at least in broad strokes. The four inner rocky planets, Mercury, Venus, Earth, and Mars, orbit within about 228 million kilometers of the Sun. The four outer gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, extend the system to about 4.5 billion kilometers. Neptune, the outermost planet, orbits at roughly 30 astronomical units from the Sun. 1 astronomical unit, again, is the Earth-Sun distance, about 150 million kilometers. So the planetary system, from Mercury to Neptune, spans roughly 30 astronomical units. But the solar system does not end at Neptune, not even close. Beyond Neptune lies the Kuiper Belt, a ring of icy bodies stretching from about 30 to roughly 50 astronomical units. Pluto, reclassified as a dwarf planet in 2006, is one of the largest objects in this region. The Kuiper Belt contains an estimated 100,000 objects larger than 100 kilometers across, along with billions of smaller bodies. It is the source of short-period comets, comets with orbital periods of less than 200 years, that periodically sweep through the inner solar system, trailing their characteristic tails of gas and dust. Beyond the Kuiper Belt, extending to perhaps 1,000 astronomical units, lies the scattered disk, a more loosely bound population of icy objects with highly elliptical and inclined orbits. These objects were likely scattered outward by gravitational interactions with Neptune during the early history of the solar system. And beyond the scattered disk, extending outward to distances of 20,000, 50,000, perhaps 100,000 astronomical units, lies the Oort cloud. This is the critical structure in the story of Gliese 710. The Oort cloud was proposed in 1950 by the Dutch astronomer Jan Oort. He noticed that long-period comets with orbital periods of thousands or millions of years, seem to come from all directions, not just from the plane of the solar system. This suggested that they were falling inward from a spherical shell surrounding the Sun at vast distances. Oort calculated that this shell must extend to distances of about 50,000 to 100,000 astronomical units, roughly 1 light-year, and must contain billions, perhaps trillions, of icy bodies. No object in the Oort cloud has ever been directly observed. The bodies there are too small, too faint, and too far away for any existing telescope to detect. The nearest Oort cloud object is probably thousands of astronomical units from the Sun, and at that distance, a comet-sized body would be billions of times too faint to see. Everything we know about the Oort cloud is inferred from the comets that fall inward from it, tracked by patient observers as they swing through the inner solar system on their million-year orbits. Here is a scaled comparison that helps convey the staggering size of the Oort cloud. If you shrank the solar system so that the Earth's orbit was the size of a dinner plate, about 25 centimeters across, then Neptune would be a ring about 7.5 meters from the center. The Kuiper Belt would extend to about 12 meters, and the outer edge of the Oort cloud would be roughly 250 kilometers away. The planetary system is the dinner plate. The Oort cloud is a sphere larger than a small country. The part of the solar system that most people think of, planets, moons, asteroids, is vanishingly tiny compared to the Oort cloud. It is the difference between a house and a continent. The total mass of the Oort cloud is estimated at somewhere between 1 and 100 Earth masses, distributed among trillions of objects, ranging from pebbles to bodies tens or hundreds of kilometers across. These objects are composed primarily of water ice, along with frozen carbon dioxide, methane, and ammonia mixed with dust and rock. They are the leftovers of the solar system's formation, bodies that condensed from the solar nebula 4.6 billion years ago, but were ejected to enormous distances by gravitational interactions with the giant planets, particularly Jupiter. They have been sitting out there, in the deep cold of interstellar space, barely warmed by the distant sun, for almost the entire history of the solar system. The temperature in the Oort cloud is approximately 10 to 20 Kelvin, roughly -250 to -260 degrees Celsius. At these temperatures, all volatile substances are frozen solid. There is no liquid water, no flowing gas, no weather, no geology, just ice and rock and darkness, drifting in stable orbits around a sun so distant that it appears as just another bright star in the sky. A bright star, yes, but not obviously brighter than many others. From the outer Oort cloud, the sun would provide no perceptible warmth. You would need a telescope to distinguish it from the background stars. And it is this vast, dark, silent reservoir that Gliese 710 will pass through. To understand how the Oort cloud formed, we need to go back to the birth of the solar system itself. Approximately 4.6 billion years ago, the sun and its planets condensed from a vast cloud of gas and dust called the solar nebula. As the planets grew, their gravity became powerful enough to fling smaller bodies outward. Jupiter, the largest planet, was the primary agent of this ejection. Its immense gravitational influence scattered billions of icy bodies, planetesimals that had formed in the cold outer regions of the solar nebula, onto elongated orbits that carried them far from the Sun. Over millions of years, the gravitational influence of passing stars and the galactic tide gradually circularized some of these orbits, trapping the scattered bodies in a spherical shell at distances of tens of thousands of astronomical units. The Oort cloud was born, not from material that formed in place, but from material that was violently ejected from the region of the planets and then gently captured at the solar system's edge. This formation mechanism has an important consequence. The composition of Oort cloud objects should be similar to the composition of objects that formed in the outer solar system. The Kuiper Belt objects, the moons of the giant planets, the comets we observe today. They are made of water ice, carbon dioxide ice, ammonia ice, methane ice, and silicate dust. They are the frozen building blocks of planets that never formed, the leftover debris of solar system construction preserved in the deepest cold of interstellar space for billions of years. Some researchers have proposed that the Sun may have captured Oort cloud material from other stars. When the Sun was young, it was part of a birth cluster, a group of stars that formed together from the same molecular cloud. In the dense environment of the birth cluster, stars were close together, and their Oort clouds may have overlapped or exchanged material. Simulations by Hal Leveson, Ramon Brasser, and others suggest that a significant fraction of the current Oort cloud, perhaps as much as 90%, may have been captured from the disks around other stars in the birth cluster, rather than formed from the Sun's own disk. If this is true, then the Oort cloud is not entirely ours. It is a cosmopolitan collection, assembled from the debris of multiple stellar systems during the Sun's infancy. The Oort cloud's great distance from the Sun makes it gravitationally vulnerable. The Sun's gravitational influence weakens with distance. It falls off as the square of the distance, following Newton's law. At 50,000 astronomical units, the Sun's gravity is roughly 2.5 billion times weaker than it is at Earth's distance. Objects there are barely bound. Their orbital velocities are measured in meters per second, walking speed. A gentle gravitational nudge from a passing star or from the tidal pull of the galaxy itself can shift an Oort cloud object from a stable orbit to one that plunges deep into the inner solar system. This is in fact how long-period comets are produced. They are not new objects, they are ancient ones, disturbed from their cold, stable rest by external gravitational perturbations. The galaxy provides a slow, constant perturbation, the galactic tide, caused by the gravitational pull of the overall mass distribution of the Milky Way. This tide slowly and continuously changes the orbits of Oort cloud objects, sending some inward, pushing some outward. It is the dominant source of long-period comets under normal conditions. But a close stellar encounter is not a normal condition. It is a discrete, powerful event that can override the gentle galactic tide and produce a dramatic spike in cometary activity. And that is exactly what Gliese 710 will do. The question is, how dramatic? How many comets will be dislodged? How many will reach the inner solar system? How many will cross Earth's orbit? And how does this compare to the impact that killed the dinosaurs? To answer these questions, we need to look more closely at the star itself. What is Gliese 710? How big is it? How fast is it moving? And how precisely do we know its trajectory? The answers to these questions have changed significantly over the past 2 decades, as our instruments have improved, and the story of how those answers were refined is in its own right a remarkable tale of scientific precision. Gliese 710 is named after its entry in the Gliese catalogue of nearby stars, a catalogue compiled by the German astronomer Wilhelm Gliese, starting in 1957 and updated in subsequent editions. The star is also known by other catalogue designations, HIP P 89825 in the Hipparcos catalogue, and various other labels in various other surveys. It is a K-type main sequence star, sometimes described as an orange dwarf. It has roughly 60% the mass of our Sun, about 67% of the Sun's radius, and a surface temperature of approximately 4,250 Kelvin, compared to the Sun's 5,770 Kelvin. It is dimmer than the Sun, emitting only about 4% as much light. If you were standing on a hypothetical planet at the same distance the Earth orbits the Sun, Gliese 710 would appear as a dim, reddish-orange disk in the sky, providing far less warmth and light than our Sun. At its current distance of 64 light-years, Gliese 710 is invisible to the naked eye. Its apparent magnitude is roughly 9.7, well below the threshold of human vision, which is limited to about magnitude 6 under the best conditions. You would need binoculars or a small telescope to see it. It is, by every measure, an ordinary, unremarkable star, one of hundreds of billions in the Milky Way. There is nothing special about its size, its colour, its temperature, or its composition. What makes it special is its trajectory. The first suggestion that Gliese 710 might make a close approach to the Sun came in 1999 from a study by the astronomers Joan Garcia Sanchez and Robert Preston, among others, who used data from the Hipparcos satellite, the European Space Agency's first dedicated astrometry mission, launched in 1989. Hipparcos measured the positions, distances, and motions of over 100,000 stars with unprecedented accuracy. By combining these measurements with radial velocity data, the speed at which a star moves toward or away from us, measured by the Doppler shift of its spectral lines, Garcia Sanchez and colleagues identified a number of stars that would make relatively close approaches to the Sun over the next few million years. Gliese 710 was among the closest. The initial Hipparcos-based estimate placed the closest approach at roughly 1.4 light-years, or about 88,000 astronomical units. This was close by interstellar standards, but well outside the denser inner regions of the Oort cloud. The result was noteworthy, but not alarming. Then, in 2013, the European Space Agency launched the Gaia satellite. Gaia is in many ways the successor to Hipparcos, but it operates on an entirely different scale. While Hipparcos measured about 100,000 stars, Gaia is measuring the positions and motions of nearly 2 billion. Its positional accuracy is measured in micro-arcseconds, millionths of an arcsecond, where 1 arcsecond is 1/3600th of a degree. To put this in perspective, 1 microarcsecond is the angle subtended by a human hair seen from a distance of roughly 1,000 kilometers. Gaia's measurements are so precise that they can detect the wobble of a star caused by an orbiting planet at distances of hundreds of light-years. When Filip Bersky and Piotr Dybczynski at Adam Mickiewicz University in Poland applied Gaia's data to the trajectory of Gliese 710, the result was startling. The closest approach distance shrank dramatically, from about 1.4 light-years to approximately 10,360 astronomical units. That is roughly 1/6 of a light-year. The star would not merely graze the outer Oort cloud, it would plunge deep into its interior. This was not a minor revision. It was a factor of 8 reduction in the closest approach distance. And because the gravitational perturbation on Oort cloud objects depends strongly on how close the passing star comes, the implications for cometary injection into the inner solar system changed dramatically as well. The speed of the encounter also matters. Gliese 710 is approaching the Sun at a radial velocity of approximately -13.8 kilometers per second, meaning it is moving toward us at about 13.8 kilometers per second along the line of sight. Its total space velocity relative to the Sun is approximately 14 to 15 kilometers per second. For comparison, the Sun's orbital velocity around the galaxy is about 220 kilometers per second. Gliese 710 is moving relatively slowly, which is actually worse from the standpoint of gravitational perturbation. A fast-moving star would zip through the Oort cloud quickly, giving its gravity less time to act. A slow-moving star lingers, allowing its gravitational influence to accumulate over a longer period. Gliese 710 is, in this sense, the worst kind of visitor, close and slow. The encounter will not happen tomorrow. It is projected to occur approximately 1.3 million years in the future, with an uncertainty of a few tens of thousands of years. That is an inconceivable span of time by human standards. 1.3 million years ago, Homo erectus was walking the African plains. Modern humans did not yet exist. Agriculture would not be invented for another 1.29 million years. The encounter with Gliese 710 lies so far in the future that predicting the state of human civilization at that point is impossible. We may not exist. We may have spread across the galaxy. We may have evolved into something unrecognizable. But the star does not care about our plans. It is on its way regardless. And this raises the question that drives the rest of our inquiry. What exactly will happen when Gliese 710 arrives? What will its gravity do to the Oort cloud? How many comets will be sent tumbling toward the inner solar system? And is there any chance at all, that one of them could threaten the Earth? But here is the deeper concern, the one that astronomers do not always emphasize in public. Gliese 710 is the closest predicted stellar encounter in the next few million years. But it is not the only one. Gaia's data has revealed dozens of stars that will pass within a few light years of the Sun over the next 10 million years. The galaxy is not empty. It is full of stars, all in motion, all following their own orbits, and our solar system sits in their path like a pebble on a busy road. The question is not whether another star will come close. The question is when and how close, and what it will disturb when it arrives. The core problem is not that Gliese 710 is dangerous in the immediate cinematic sense. It will not collide with the Sun. It will not scorch the Earth. It will not even be visible to the naked eye from Earth's surface at closest approach, though it will be considerably brighter than it is now, reaching perhaps third magnitude, a moderately bright star in the night sky. The core problem is subtler, slower, and in some ways more terrifying because of its subtlety. The problem is the Oort cloud. As we described earlier, the Oort cloud is a vast spherical shell of icy bodies surrounding the Sun at distances of roughly 2,000 to 100,000 astronomical units. The total number of objects in the Oort cloud larger than 1 kilometer is estimated to be in the trillions. Some estimates place the number as high as several trillion. Most of these objects are small, a few kilometers across or less, but some may be considerably larger, perhaps tens or even hundreds of kilometers in diameter. These are not asteroids. They are comets, or rather, potential comets, frozen and dormant in the deep cold, waiting for a gravitational disturbance to send them sunward. Under normal conditions, the Oort cloud loses comets at a slow, steady rate. The galactic tide, the gravitational influence of the overall mass of the Milky Way, gently perturbs the orbits of Oort cloud objects, sending a trickle of them inward. Giant molecular clouds, massive concentrations of gas and dust drifting through the galaxy, also perturb the Oort cloud when they pass nearby. These processes produce a roughly constant background rate of long-period comets entering the inner solar system. On average, approximately 1 to 2 new long-period comets are discovered per year, and the total rate of long-period comets brighter than absolute magnitude 11 entering the inner solar system is estimated at roughly 5 to 10 per year. But a close stellar flyby is a different kind of event. It is a concentrated, powerful gravitational perturbation delivered over a timescale of tens of thousands of years, the time it takes the passing star to traverse the Oort cloud, and its effects are not uniform. The side of the Oort cloud closest to the passing star is pulled harder than the far side, creating a tidal effect. Objects near the star's trajectory are strongly perturbed. Objects far from it are less affected. The result is a complex, asymmetric reshuffling of cometary orbits, with some objects being ejected from the solar system entirely, some having their orbits widened or narrowed, and some, the crucial ones, being deflected onto orbits that bring them into the inner solar system. The number of comets injected into the inner solar system by a stellar flyby depends on several factors. The most important are the distance of closest approach, the mass of the passing star, and its velocity relative to the Sun. A closer, more massive, slower-moving star produces a stronger perturbation and injects more comets. Gliese 710, as we have noted, is relatively close, moderately massive, about 60% of the Sun's mass, and slow. This combination makes it an exceptionally effective perturber. There is a useful way to quantify the strength of a stellar perturbation. Physicists use a parameter called the impulse, essentially the total change in velocity that the passing star imparts to an Oort cloud object during the encounter. The impulse depends on the distance of closest approach, the mass of the star, and the speed of the encounter. For Gliese 710, the impulse on objects at distances of 10,000 to 20,000 astronomical units from the Sun is substantial, on the order of meters per second or more. This may sound tiny, but remember that Oort cloud objects are barely bound to the Sun. Their orbital velocities at 30,000 astronomical units are roughly 100 meters per second. A perturbation of even a few meters per second can change their orbits significantly, pushing some into Earth-crossing trajectories. To put this in a scaled comparison, imagine you are balancing a marble on the rim of a bowl. A slight breath of air, a tiny push, can send the marble rolling down into the bowl. The Oort cloud objects are like those marbles, balanced on the gravitational rim of the solar system. Gliese 710's passage is the breath of air. Most marbles will stay on the rim. Some will roll outward and fall off, lost to interstellar space. But some will roll inward, toward the center, toward the Sun, toward the planets. The total number of objects dislodged depends on how many marbles are sitting on the rim, which brings us back to the central uncertainty. How many objects are in the Oort cloud? Simulations performed by Debchinsky and Bersky and independently by other research groups have modeled the encounter in detail. The results vary depending on the assumptions made about the structure and density of the Oort cloud, but the general picture is consistent. Gliese 710's passage will significantly increase the flux of long-period comets entering the inner solar system. The increase will not be sudden. It will build up over hundreds of thousands of years as the perturbed comets slowly fall inward on their new orbits, and it will persist for millions of years after the encounter. The peak of the comet shower is expected to arrive between 2 and 4 million years after the closest approach, roughly 3 to 5 million years from now. Why is there such a long delay? Because the Oort cloud is far away and the comets fall inward slowly. A comet perturbed from an orbit at 20,000 astronomical units will take approximately 2 million years to reach the inner solar system. It must travel the entire distance from the outer solar system to the region of the planets, accelerating gradually under the Sun's gravity. The journey is long, silent, and invisible. The comet will not begin to outgas and develop a visible tail until it approaches within roughly 5 astronomical units of the Sun, well inside the orbit of Jupiter. Until that point, it is just a dark chunk of ice and rock moving through the void, undetectable by any telescope. This means that when the comet shower from Gliese 710 finally arrives, it will come as a surprise, not to the astronomers who predicted it, but to whatever beings are alive to witness it. The star will have passed through and departed millions of years earlier. Its gravitational fingerprints will have long since faded from the Oort cloud, but the comets it dislodged will still be falling, one by one, into the warm inner solar system, like seeds shaken from a tree by a wind that blew long ago. The numbers are striking. Some simulations predict that the encounter could increase the rate of long-period comets entering the inner solar system by a factor of 10 or more, relative to the current background rate. Others suggest more modest increases, depending on the assumed density of the Oort cloud. But even a modest increase, a doubling or tripling of the cometary flux, could have significant consequences over geological timescales. But here's the problem. We do not know the density or structure of the Oort cloud with any precision. We have never observed it directly. We have never sent a spacecraft to it. The Voyager probes, the most distant human-made objects, are currently at roughly 165 astronomical units from the Sun, less than 1% of the distance to the inner Oort cloud. Everything we know about the Oort cloud is inferred from the comets that fall inward from it, and those comets represent a tiny, biased sample of the total population. It is like trying to estimate the number of fish in the ocean by counting the ones that wash up on a single beach. The estimates of Oort cloud population range widely. Some models place the total number of objects larger than 1 kilometer at about 100 billion. Others suggest several trillion. The mass estimates range from about 1 Earth mass to 100 Earth masses. The radial distribution, how many objects are at what distance, is even more uncertain. Some models favor a concentration toward the inner Oort cloud at distances of 20,000 to 30,000 astronomical units. Others favor a more uniform distribution. The choice of model significantly affects the predicted outcome of the Gliese 710 encounter. And it gets worse. The effects of a cometary shower are not limited to the immediate danger of impacts. A sustained increase in cometary flux changes the entire inner solar system. Comets that pass close to the giant planets can be captured into shorter period orbits, becoming new members of the Jupiter family or Saturn family cometary populations. Some of these captured comets will eventually disintegrate, producing new meteor streams. Others will continue to orbit for thousands or millions of years, gradually evolving and occasionally crossing the orbits of the terrestrial planets. The inner solar system becomes a busier, more cluttered, more hazardous place. There is also the question of dust. When a comet enters the inner solar system and approaches the Sun, solar heating causes its ices to sublimate, to transform directly from solid to gas. This outgassing carries dust particles with it, releasing them into interplanetary space. Over time, this cometary dust accumulates in the inner solar system, forming a diffuse cloud called the zodiacal dust cloud. The zodiacal cloud is already visible. It produces a faint glow called the zodiacal light, visible after sunset or before sunrise in dark skies. A tenfold increase in cometary flux would significantly increase the density of the zodiacal dust cloud, potentially dimming the sunlight reaching Earth by a small but measurable amount. Some researchers have speculated that past comet showers may have contributed to climate cooling on Earth through this mechanism, though the evidence is not yet conclusive. Cometary dust falling into Earth's atmosphere could also have chemical effects. Comets are rich in organic molecules, amino acids, nucleotide bases, polycyclic aromatic hydrocarbons, the building blocks of life. A sustained rain of cometary dust could deliver significant quantities of organic material to the Earth's surface and upper atmosphere. Whether this would have beneficial or harmful effects on existing life is an open question. It might seed the atmosphere with chemicals that react with ozone, thinning the protective layer that shields the surface from ultraviolet radiation. Or it might deliver exotic chemistry that interacts with Earth's biosphere in unpredictable ways. The effects of a cometary shower extend far beyond the simple question of impacts. They touch on climate, chemistry, and the long-term evolution of the Earth's environment. There is also the question of large objects. The Oort cloud is expected to contain a small number of bodies much larger than typical comets, objects tens or hundreds of kilometers across. If even one such object were deflected onto an Earth-crossing orbit, the consequences would be catastrophic on a scale that dwarfs the Chicxulub impact. A body 100 kilometers across striking the Earth would release energy equivalent to roughly 100 million times the Chicxulub impact. It would sterilize the surface of the planet. It would vaporize the oceans. It would end not just a chapter of life, but possibly the entire story. The probability of such an event is extremely low. Even in the most pessimistic models of the Gliese 710 encounter, the chance of a large Oort cloud body striking Earth is measured in millionths or billionths, but the probability is not zero. And when the consequence of an event is the extinction of all complex life on Earth, even an extremely small probability demands attention. To understand why, it helps to examine what happens when a comet enters the inner solar system. A typical long-period comet begins its inward journey from a distance of perhaps 30,000 astronomical units. At that distance, it is moving at roughly a few meters per second relative to the Sun, walking pace, but as it falls inward, the Sun's gravity accelerates it. By the time it crosses the orbit of Neptune, at 30 astronomical units, It is traveling at roughly 5 to 6 kilometers per second. By the time it crosses the orbit of Jupiter, at 5 astronomical units, it has accelerated to approximately 13 kilometers per second. And by the time it reaches Earth's orbit, at 1 astronomical unit, it is moving at roughly 42 kilometers per second, fast enough to cross the entire diameter of the Earth in about 5 minutes. At these speeds, even a small body carries enormous kinetic energy. A comet 1 kilometer in diameter, traveling at 40 kilometers per second, carries kinetic energy roughly equivalent to 100 million tons of TNT, roughly 2,000 times the energy of the largest nuclear weapon ever detonated. A 10-kilometer comet carries energy roughly 1 million times greater. These numbers are not theoretical. They are simple physics. The kinetic energy of a moving body equals 1/2 times its mass times the square of its velocity. The velocity is fixed by orbital mechanics. The mass is fixed by the size and density of the comet. The energy follows inevitably. And comets, unlike asteroids, come fast. Near-Earth asteroids typically approach Earth at speeds of 15 to 25 kilometers per second. Long-period comets, falling in from the outer solar system on near-parabolic orbits, arrive at 35 to 70 kilometers per second. At these higher velocities, a comet of a given size carries roughly 4 to 10 times the kinetic energy of an asteroid of the same size. The comet threat is, kilogram for kilogram, more energetic than the asteroid threat. There is a common misconception that Jupiter acts as a cosmic shield, protecting the inner planets from cometary bombardment. The idea is that Jupiter's immense gravity, it is 318 times the mass of Earth, captures or deflects incoming comets before they can reach the inner solar system. This notion has been repeated in popular science for decades, and it contains a grain of truth. Jupiter does indeed deflect some incoming bodies. It gravitationally captures some comets into short-period orbits, preventing them from making repeated passes through the inner solar system. The comet Shoemaker-Levy 9, which famously crashed into Jupiter in July of 1994, was one such captured comet. Its fragments struck the giant planet with the force of millions of nuclear weapons, creating dark scars in Jupiter's atmosphere visible from Earth through modest telescopes. But research over the past 2 decades has complicated this picture. Studies by Brett Gladman, Jonathan Horner, and others have shown that Jupiter's effect is more ambiguous than previously thought. While Jupiter deflects some comets away from Earth, it also gravitationally focuses others toward the inner solar system. It can capture comets from long-period orbits into shorter-period ones, keeping them in the inner solar system longer and increasing the probability of an impact over time. In some simulations, removing Jupiter from the solar system actually decreases the rate of cometary impacts on Earth. In others, it increases them. The net effect depends sensitively on the population of comets being considered, their orbital parameters, and the timescale of the analysis. What is clear is that Jupiter does not provide anything close to complete protection. Long-period comets entering the inner solar system at high velocity and on hyperbolic trajectories pass through too quickly for Jupiter's gravity to reliably deflect them. The shielding effect, to the extent that it exists, applies primarily to short-period comets, not to the long-period comets that a stellar flyby would inject from the Oort cloud. Gliese 710's comet shower would largely bypass Jupiter's protective influence. There is another factor that amplifies the threat from long-period comets, and it is one that is often overlooked. Long-period comets are, in general, larger than the average near-Earth asteroid. The population of near-Earth asteroids is dominated by small bodies. Most are less than 100 meters across, and the number drops off steeply with size. By contrast, the Oort cloud is believed to contain a significant population of bodies several kilometers to tens of kilometers across, and possibly some that are hundreds of kilometers in diameter. The largest known trans-Neptunian objects, bodies like Eris, Makemake, and Sedna, which orbit in the distant reaches of the solar system, are hundreds to thousands of kilometers across. Some of these objects may be inner Oort cloud members, and their existence suggests that the Oort cloud contains a population of large bodies that has no counterpart in the near-Earth asteroid population. If the Gliese 710 encounter sends even a small number of these large bodies onto orbits that bring them into the inner solar system, the consequences could be severe. A body the size of Sedna, roughly 1,000 kilometers in diameter, striking the Earth would be an extinction-level event of a magnitude never experienced in the history of complex life. It would not merely trigger a mass extinction, it would likely sterilize the planet's surface entirely, melting the crust, boiling the oceans, and destroying the atmosphere. Recovery, if it occurred at all, would take hundreds of millions of years. Again, the probability of such an extreme event is vanishingly small, but the exercise is important because it illustrates the asymmetry at the heart of the problem. The probability is tiny, the consequence is total, and over millions of years, small probabilities can translate into significant cumulative risks. Let us also consider an effect that is rarely discussed outside the technical literature, but is highly relevant to the Gliese 710 encounter: the perturbation of the inner Oort cloud. Most discussions of the Oort cloud focus on the outer Oort cloud, at distances of 20,000 to 100,000 astronomical units, but there is also an inner Oort cloud, sometimes called the Hills cloud, extending from roughly 2,000 to 20,000 astronomical units. This region is closer to the Sun, and its objects are more tightly bound gravitationally. Under normal conditions, the galactic tide is too weak to significantly perturb objects in the inner Oort cloud. They sit in stable orbits, undisturbed, for billions of years, but a close stellar passage can reach them. Gliese 710, at a closest approach of roughly 10,000 astronomical units, will pass directly through the inner Oort cloud. Its gravitational influence will be far stronger there than in the outer cloud, because the perturbation scales with the inverse square of the distance. Objects in the inner cloud will experience gravitational tugs far larger than anything they have experienced in billions of years. Some of them will be shifted onto new orbits. Some of those new orbits will be sunward. The inner Oort cloud is thought to contain far more mass than the outer cloud, perhaps 10 times as much, or even more. If this is correct, then the Gliese 710 encounter could mobilize a far larger reservoir of cometary material than models based on the outer cloud alone would suggest. The comet shower could be more intense, more prolonged, and more dangerous than the baseline predictions indicate. Something is wrong with our assumptions if we think the outer Oort cloud is the only concern. The inner cloud, with its greater mass and its closer proximity to the passing star, may be the real source of danger, and we know even less about it than we know about the outer cloud. Let us now place this in historical context. Gliese 710 is not the first star to pass close to the Sun. It is not even the first in the astronomical record. Stellar encounters are a natural and ongoing feature of galactic dynamics. They have been happening for the entire 4.6 billion year history of the solar system, and they will continue for as long as the Sun exists. In 2015, Eric Mamajek and colleagues announced the discovery that a small red dwarf star called Schultz's star, accompanied by a brown dwarf companion, had passed through the outer Oort cloud approximately 70,000 years ago. The closest approach distance was estimated at about 52,000 astronomical units, roughly 0.82 light-years. This was the closest known stellar flyby in the history of our solar system. The encounter occurred so recently, in geological terms, that early modern humans were alive when it happened. Our ancestors may have looked up at the night sky and seen this dim, reddish intruder, though at its closest it would still have been far too faint for the naked eye. Schultz's star is much smaller than Gliese 710, only about 86% of the mass needed to sustain hydrogen fusion, making it just barely a star, and its passage was at a much greater distance and a higher velocity. Its gravitational effect on the Oort cloud was relatively modest, but it served as a powerful reminder. The solar system has had close visitors before, and it will have them again. The discovery of Schultz's star also illustrates how recently we have developed the tools to detect such encounters. Without precise astrometric data and radial velocity measurements, we would have no way of knowing that this star had passed through the Oort cloud 70,000 years ago. For the vast majority of human history, and indeed for the vast majority of the solar system's history, Close stellar encounters came and went, without any observer being aware of them. The comets they perturbed fell inward silently, without announcement, without warning, without anyone knowing why the night sky had suddenly acquired a new bright visitor. The connection between passing stars and cometary showers was invisible. It could only be understood by a civilization capable of measuring the three-dimensional motions of thousands of stars with extraordinary precision. We are that civilization, and we have held this capability for less than 50 years. In the 4.6 billion year history of the solar system, the window during which anyone has been able to predict a stellar encounter is roughly 1/10 millionth of the total time. We are looking through a pinhole in time, catching a glimpse of a process that has been running since before the Earth existed. Studies using Gaia data have identified other future close approaches as well. The star GJ208, an orange dwarf, will pass within about 1.6 light-years of the Sun in roughly 1.6 million years. The star HIP 85605 will come within about 1.2 light-years in roughly 300,000 years. None of these approaches is as close or as significant as Gliese 710, but they illustrate the broader point. The solar system exists in a dynamic environment, and close stellar passages are a regular occurrence. The question that emerges from all of this is unsettling in its simplicity. Has a past stellar encounter, millions or tens of millions of years ago, already sent a large cometary body on a long, slow inward trajectory, one that has not yet arrived? Is there, right now, somewhere in the darkness between the Oort cloud and the orbit of Neptune, a large icy body drifting slowly sunward, perturbed from its ancient orbit by a star that passed nearby millions of years ago? We would not see it. We cannot survey the Oort cloud. We cannot track objects at those distances. The comet could be 50 kilometers across, and we would have no way of knowing it was coming until it reached the inner solar system, by which time there might be only a few years or decades of warning. This is not a hypothetical concern designed to frighten. It is a direct consequence of the physics. Long-period comets, by definition, have orbital periods measured in millions of years. A comet perturbed from the Oort cloud 2 million years ago might not reach the inner solar system for another million years. The pipeline between a stellar encounter and its consequences is measured in geological time. And we have only been watching the sky with modern instruments for a few centuries. The delay between perturbation and arrival creates an insidious problem for planetary defense. Consider a concrete scenario. Suppose that a past stellar encounter, one that occurred 5 million years ago, long but before any human existed, perturbed a body 30 kilometers across from its stable orbit in the Oort cloud. That body is now falling inward on a highly elliptical orbit that will bring it through the inner solar system. It is currently somewhere between the Oort cloud and the orbit of Neptune, perhaps 10,000 astronomical units from the Sun. At that distance, it is far too faint to detect. It reflects no sunlight, it emits no radiation. It is a dark, cold, silent projectile, moving at a few hundred meters per second, drifting closer every day. It will reach the orbit of Neptune in perhaps 200,000 years. It will reach the orbit of Jupiter in perhaps 250,000 years. It will reach the orbit of Earth in perhaps 260,000 years. And at no point during this journey will it be detectable by any current or planned astronomical survey until it enters the inner solar system and begins to outgas, perhaps 1 to 2 years before its closest approach to the Sun. 1 to 2 years of warning. For a body 30 kilometers across, moving at perhaps 50 kilometers per second, at that speed, it would cross the Earth's diameter in about 4 minutes. At that size, it would deliver energy roughly 100 times that of the Chicxulub impactor. And with 1 to 2 years of warning, there would be nothing, absolutely nothing, that current technology could do to stop it. This is not the Gliese 710 scenario. This is the scenario that may already be underway from a past encounter we know nothing about. The Gliese 710 encounter will add to this background risk, piling new perturbations on top of old ones, but the fundamental vulnerability exists regardless of Gliese 710. The Oort cloud is a loaded gun, and the galaxy is constantly pulling the trigger. But here's what makes this truly terrifying. We are not just dealing with one encounter, we are dealing with a cumulative process. Every close stellar passage over the 4.6 billion year history of the solar system has perturbed the Oort cloud. Every passage has injected comets. The current rate of long-period comets entering the inner solar system is the sum of all past perturbations, the galactic tide, past stellar flybys, past encounters with molecular clouds. The Gliese 710 encounter will add to this sum. It will pile new comets on top of the ones already falling inward. And in 1.3 million years, when the star arrives, the process will intensify. So what have scientists done to understand the threat? What models have they built? What simulations have they run? And what do the results tell us about the future of our solar system? The study of close stellar encounters and their effects on the Oort cloud is a relatively young field, but it has advanced rapidly in the past 2 decades, driven by increasingly precise data and increasingly powerful computers. Let us examine the major approaches, their findings, and their limitations. The first approach is direct numerical simulation of the Oort cloud. In this method, researchers create a computer model of the Oort cloud, populating it with millions or billions of test particles, virtual comets, distributed according to some assumed radial and angular distribution. They then simulate the gravitational effect of a passing star, integrating the equations of motion for each particle forward in time and tracking which particles end up on orbits that enter the inner solar system. The pioneering work in this area was done by Piotr Dybczynski and his colleagues at Adam Mickiewicz University in Poznan, Poland. Using data first from Hipparcos and later from Gaia, Dybczynski systematically identified the stars most likely to perturb the Oort cloud and modelled their effects. His simulations of the Gliese 710 encounter, published in a series of papers from 2002 onward, showed that the star's passage would produce a significant but not catastrophic comet shower. The number of comets injected into the inner solar system depended heavily on the assumed structure of the Oort cloud, but in most models, the increase in cometary flux was substantial, a factor of several to perhaps 10 times the background rate. One of the key findings of these simulations is that the timing of the comet shower is delayed relative to the closest approach. The star passes through the Oort cloud in roughly 100,000 years, but the comets it perturbs do not arrive in the inner solar system immediately. They must travel from distances of tens of thousands of astronomical units to a few astronomical units on highly elliptical orbits. This journey takes millions of years. The peak of the shower is expected roughly 2 to 4 million years after the closest approach, meaning the maximum cometary flux from the Gliese 710 encounter would arrive approximately 3 to 5 million years from now. This delay has an important implication. The danger from Gliese 710 is not an immediate concern for current human civilization. Even if the encounter were happening tomorrow, the comet shower would not begin for millions of years. But this should not be a source of complacency. The delay means that comets perturbed by past stellar encounters that occurred millions of years ago, could be arriving now. We could be in the tail end of a comet shower triggered by a star that passed through the Oort cloud long before humans evolved, and we would have no way of knowing it from the cometary flux alone. The second approach to understanding the Gliese 710 encounter involves analytic and semi-analytic models. These are mathematical frameworks that approximate the gravitational perturbation using simplified equations rather than tracking individual particles. They are less detailed than full numerical simulations, but can explore a wider range of parameters and provide insight into the underlying physics. One important result from these models concerns the so-called loss cone. In the context of Oort cloud dynamics, the loss cone is the region of orbital parameter space that corresponds to comets with orbits that bring them into the inner solar system. Under normal conditions, when only the galactic tide is operating, the loss cone is gradually replenished as the tide shifts cometary orbits. But a stellar flyby can suddenly fill the loss cone, dumping a large number of comets into the inner solar system in a relatively short burst. The size and duration of this burst depend on the parameters of the encounter: distance, mass, velocity, and on the pre-existing state of the Oort cloud. Analytic models developed by researchers including Julio Fernandez, Hans Rickman, and others have shown that the Gliese 710 encounter will produce what is called a strong perturbation of the Oort cloud. This means that the star's gravity will dominate over the galactic tide during the encounter, producing a comet shower that is significantly above the background rate. The models predict a peak increase in cometary flux of roughly 5 to 15 times the current rate, lasting for 1 to 2 million years. To understand why this matters, consider what a factor of 10 increase means in concrete terms. Currently, roughly 5 to 10 long-period comets per year enter the inner solar system brightly enough to be detected. If this rate increases by a factor of 10, then 50 to 100 long-period comets per year will be entering the inner solar system. Over 1 million years, that is 50 to 100 million comets. The vast majority of these will pass harmlessly through the inner solar system, swinging around the sun and returning to the outer dark. But the probability that any individual comet will hit any individual planet is not zero. For Earth, the impact probability for any single random long-period comet is roughly 1 in a billion per perihelion passage. But with 100 million comets passing through over a million years, the probability of at least one impact on Earth during the shower rises to roughly 1 in 10. That is not a comfortable number, and this estimate is conservative. It assumes that all the comets are small, a few kilometers across or less. If the shower includes even a handful of large bodies, 10, 20, 50 kilometers across, the consequences of a single impact could be severe enough to render the probability calculation almost irrelevant. When the stake is planetary sterilization, 1 in 10 is not reassuring. There is an additional subtlety that the analytic models capture. The loss cone does not refill uniformly. After a stellar flyby, the loss cone is suddenly flooded with comets, producing a burst of activity. But the comets that are injected first are the ones that were already closest to the loss cone boundary, the ones whose orbits were already nearly Earth-crossing. These arrive first, producing a sharp initial spike. The comets that were farther from the loss cone take longer to be shifted into Earth-crossing orbits, producing a prolonged tail of activity that can last millions of years. The shower is not a single wave. It is a sharp spike followed by a long, slow decline, and during that long decline, the cometary flux remains elevated above the background rate, meaning that the inner solar system is busier and more hazardous than usual for a very long time. The third approach involves looking backward, searching for evidence of past cometary showers in the geological and cratering record on Earth and other bodies in the inner solar system. The idea that comet showers leave traces in the geological record has been debated for decades. In 1984, the paleontologists David Raup and Jack Sepkoski published a controversial paper claiming to have found a roughly 26 million year periodicity in mass extinctions over the past 250 million years. They suggested that this periodicity might be driven by periodic comet showers, triggered by some astronomical mechanism, perhaps the oscillation of the Sun above and below the galactic plane, or the influence of a hypothetical distant companion star to the Sun, sometimes called Nemesis. The Nemesis hypothesis, proposed independently by Richard Muller and by Daniel Whitmire and Albert Jackson in 1984, suggested that the Sun has an unseen companion, a red dwarf or brown dwarf in a wide orbit, whose periodic approach to the inner solar system disturbs the Oort cloud and triggers mass extinctions. Despite extensive searches, no such companion has ever been found. The Wide Field Infrared Survey Explorer, or WISE, a NASA infrared space telescope that surveyed the entire sky in 2010 and 2011, would have detected any brown dwarf or large planet within several thousand astronomical units of the Sun. None was found. The Nemesis hypothesis is now considered extremely unlikely, though it has not been completely ruled out for very small, very distant objects. The evidence for periodic mass extinctions has also been challenged. More recent analyses, using updated databases of fossil occurrences and more sophisticated statistical methods, have found that the apparent periodicity is weaker than Raup and Sepkoski reported, and may be an artifact of incomplete sampling. The question of whether mass extinctions show a periodic pattern remains open, but the evidence is not strong enough to claim a definitive cycle. What is clear, however, is that large impacts have occurred repeatedly in Earth's history, and some of them may have been caused by long-period comets perturbed from the Oort cloud. The Chicxulub impact 66 million years ago is the most famous example. The impactor was initially thought to be an asteroid, but some researchers have argued that it may have been a long-period comet based on its estimated size, velocity, and composition. In 2021, Avi Loeb and Amir Siraj at Harvard University published a paper arguing that the Chicxulub impactor was a fragment of a long-period comet that was tidally disrupted by Jupiter's gravity during a close passage. In their model, Jupiter's tidal forces broke a large comet into smaller fragments, and one of those fragments struck the Earth. If this is correct, it suggests a direct link between Oort cloud perturbations and mass extinction events. But the Chicxulub impact is just the most famous event in a much longer record of cosmic bombardment. The geological and cratering record reveals dozens of large impact structures on Earth, some of them associated with significant biological upheaval. The Pobegai crater in Siberia, roughly 100 kilometers in diameter, was formed about 35.7 million years ago by an impactor estimated at 5 to 8 kilometers across. The Chesapeake Bay impact structure on the east coast of North America, about 85 kilometers in diameter, was formed around the same time. The near-simultaneous formation of these two large craters has led some researchers to speculate that they were caused by a comet shower, multiple bodies arriving in a tight cluster, perhaps fragments of a single larger object disrupted by tidal forces. The Manickawagan crater in Quebec, Canada, is roughly 100 kilometers across and was formed about 214 million years ago. The Sudbury Basin in Ontario is one of the largest impact structures on Earth, roughly 250 kilometers across, formed about 1.85 billion years ago. The Vredefort crater in South Africa, the largest confirmed impact structure on Earth at roughly 300 kilometers in diameter, was formed about 2.02 billion years ago. These impacts were catastrophic on a planetary scale. The Vredefort impactor was estimated at 10 to 15 kilometers across. At the time of impact, the energy released was roughly 1 billion times the energy of the largest nuclear weapon. It would have caused global firestorms, acid rain, prolonged darkness, and a mass extinction of whatever organisms existed at the time. Each of these impacts was caused by a body, asteroid or comet, that happened to cross Earth's orbit at the wrong time. And some of them may have been long-period comets, sent inward from the Oort cloud by the gravitational nudge of a passing star that is now long gone, its identity unknown, its passage unrecorded in any historical or astronomical record. The fourth approach is statistical. Rather than modeling a specific encounter, researchers ask a more general question. Given the observed density of stars in the solar neighborhood and their velocities, how often should we expect close stellar encounters, and what is the cumulative effect on the Oort cloud over the lifetime of the solar system? The answer, derived from studies by Garcia Sanchez, Dybczynski, Corinne Baylor-Jones, and others, is that a star comes within 1 parsec, roughly 3.26 light-years, of the Sun approximately once every 100,000 years. A star comes within half a parsec, about 1.63 light-years, roughly once every 500,000 years. A star comes within the distance that Gliese 710 will reach, about 1/6 of a light-year, roughly once every several million to tens of millions of years. And a truly catastrophic encounter, in which a star passes within a few thousand astronomical units, occurs roughly once every 100 million years or so. The math is striking. Over the 4.6 billion year lifetime of the solar system, there have been roughly 46,000 encounters within 1 parsec, roughly 9,000 encounters within half a parsec, roughly dozens to hundreds of encounters as close as Gliese 710, and perhaps 50 to 100 encounters within a few thousand astronomical units, close enough to significantly disrupt the inner Oort cloud. Each of these encounters has perturbed the Oort cloud. Each has injected comets into the inner solar system. Each has contributed to the cratering record on Earth, the Moon, and the other terrestrial planets. The Oort cloud is not a static reservoir. It is a dynamic, constantly stirred ocean of icy bodies, shaped by the gravitational tides of the galaxy and the individual tugs of passing stars over billions of years. Corinne Baylor-Jones at the Max Planck Institute for Astronomy in Heidelberg has conducted the most comprehensive analysis of close stellar encounters using Gaia data. In a series of papers published from 2015 onward, Baylor-Jones identified hundreds of stars that will pass within 2 parsecs of the Sun over the next 10 million years. He also looked backward, identifying stars that have passed within similar distances in the past 10 million years. The results paint a picture of a solar system that is anything but isolated. Stars pass nearby regularly, on timescales that are short compared to the age of the solar system, but long compared to human civilization. One of Baylor-Jones's most striking findings is that the rate of close encounters is not constant over time. As the Sun orbits the galaxy, it passes through regions of higher and lower stellar density. When the Sun crosses the galactic plane, which happens approximately once every 30 to 35 million years, it enters a denser region and encounters stars more frequently. This oscillation has been proposed as an explanation for the apparent periodicity in mass extinction events, though the evidence for a direct link remains contested. The rate also depends on the Sun's position relative to the spiral arms of the galaxy. The spiral arms are regions of higher density, and passage through a spiral arm increases the encounter rate. The Sun is currently located between the Sagittarius and Perseus spiral arms in a region of relatively low stellar density called the local bubble, a cavity in the interstellar medium, roughly 300 light-years across, thought to have been carved by one or more supernova explosions several million years ago. The Sun's position in this relatively sparse region may be fortunate, providing a temporary reprieve from the higher encounter rates experienced closer to the spiral arms. But the Sun will not stay in the local bubble forever. Its orbit will carry it through denser regions of the galaxy, regions where stellar encounters are more frequent and potentially more dangerous. The long-term future of the solar system, on timescales of hundreds of millions to billions of years, will be shaped not just by individual stellar encounters, but by the Sun's journey through the galaxy, a journey that carries it through environments of varying stellar density, varying encounter rates, and varying levels of gravitational perturbation. The fifth and most recent approach to understanding the encounter comes from a different angle entirely. The question of whether Gliese 710 might have planets or companions of its own. If Gliese 710 has a planetary system, the encounter becomes more complex. The planets would add their own gravitational influence to the perturbation, potentially amplifying the effect on the Oort cloud. They could also capture Oort cloud objects into orbits around Gliese 710, stripping them from the Sun's gravitational domain. Conversely, if Gliese 710 has its own reservoir of icy bodies, its own Oort cloud equivalent, the encounter could inject those foreign objects into our solar system, introducing material with a completely different chemical composition. As of the latest data, no planets have been confirmed around Gliese 710. Radial velocity surveys have placed upper limits on the mass of any close-in companions, ruling out hot Jupiters but leaving open the possibility of smaller planets or planets in wider orbits. Future observations, particularly from Gaia's continued astrometric monitoring and from dedicated radial velocity campaigns, may eventually resolve this question. But for now, the simulations treat Gliese 710 as a single star, and the encounter is modelled accordingly. The question of companions extends beyond planets. Some stars in the galaxy are members of binary or multiple star systems, orbiting each other at various distances. If Gliese 710 had an unseen companion, a brown dwarf or very low-mass star in a wide orbit, the effective gravitational influence of the system would be greater, and the perturbation of the Oort cloud would be correspondingly stronger. Brown dwarfs, with masses between roughly 13 and 80 times the mass of Jupiter, are too small to sustain hydrogen fusion but are massive enough to exert significant gravitational influence. A brown dwarf companion to Gliese 710, at a distance of, say, 100 astronomical units, would add roughly 1% to the total mass of the system. and could affect the trajectory of Oort cloud objects in its vicinity. Wide infrared surveys, including those conducted by the WISE satellite and the 2-micron all-sky survey, or 2MASS, have searched for brown dwarf companions to nearby stars. No companion to Gliese 710 has been found, but the detection limits of these surveys are not absolute, and a very low luminosity companion at a moderate distance could have been missed. The question remains open. There is also the possibility that Gliese 710 is part of a moving group, a collection of stars that formed together and are still travelling through the galaxy in roughly the same direction. If so, other members of the group might also make close approaches to the Sun in the coming millions of years, producing a series of perturbations rather than a single one. Kinematic analysis of Gliese 710's motion has not revealed a clear association with any known moving group, but the identification of moving groups is an ongoing area of research, and new associations are being discovered regularly using Gaia data. A sixth consideration, one that is often underappreciated, involves the interaction between the Gliese 710 perturbation and the galactic tide. As we noted earlier, the galactic tide is the dominant source of long-period comets under normal conditions. It operates continuously, slowly shifting cometary orbits and feeding the loss cone at a roughly constant rate. When a stellar flyby occurs, its perturbation is superimposed on the galactic tide. The two effects can reinforce each other or interfere, depending on the geometry of the encounter and the direction of the tidal force. Jibczynski and others have studied this interaction in detail. They have found that the effectiveness of a stellar flyby in injecting comets depends not just on the parameters of the encounter, but also on the current state of the galactic tide. If the tidal force happens to be aligned favorably with the direction of the stellar perturbation, the combined effect can be significantly larger than either alone. If they are misaligned, the effect can be reduced. For the Gliese 710 encounter, the relative orientation of the stellar trajectory and the galactic tidal field is known, and simulations indicate that the two effects will partially reinforce each other, producing a comet shower somewhat larger than would be expected from the stellar perturbation alone. This synergy between the galactic tide and stellar encounters is a relatively recent discovery, and it has changed the way cosmologists model the long-term evolution of the Oort cloud. The traditional picture, in which the galactic tide provides a constant drizzle of comets and stellar encounters produce occasional bursts, has been replaced by a more complex picture in which the two processes interact continuously, with each encounter leaving a lasting imprint on the structure of the Oort cloud that influences the effectiveness of subsequent encounters. There is one more factor that deserves attention, and it is perhaps the most sobering. The simulations we have described model the Oort cloud as it exists today, but the Oort cloud has been losing material for 4.6 billion years, through the galactic tide, through past stellar encounters, and through the slow diffusion of comets into the inner solar system. The Oort cloud of today is almost certainly smaller and less populated than the Oort cloud that existed when the solar system was young. Some estimates suggest that the original Oort cloud may have contained 10 to 100 times as many objects as the current one. Most of those objects have been lost, ejected from the solar system by gravitational perturbations, or sent sunward and destroyed by solar heating, or captured by the giant planets. This means that the Gliese 710 encounter, while significant, is occurring in a depleted Oort cloud. The comet shower it produces will be substantial, but it would have been far more dramatic if the encounter had occurred billions of years ago when the Oort cloud was fuller. Conversely, it also means that the early solar system, when the Oort cloud was at its peak population, was subject to far more intense cometary bombardment from stellar encounters than we experience today. The late heavy bombardment, a period of intense cratering that occurred roughly 4 billion years ago, may have been partially driven by stellar encounters perturbing a young, densely populated Oort cloud. Some recent research has challenged the traditional picture of the late heavy bombardment as a discrete event, suggesting instead that it was the tail end of a prolonged period of heavy bombardment that began with the formation of the solar system. But regardless of the details, the principle is clear. A fuller Oort cloud means more intense cometary showers, and the early solar system was far more dangerous than the one we inhabit today. Future observational campaigns will significantly refine our understanding of the Gliese 710 encounter. The Gaia satellite continues to collect data, and each new data release improves the precision of stellar positions and motions. The third data release, Gaia DR3, published in 2022, provided the most precise measurements yet. Future releases will reduce the uncertainty in the closest approach distance and timing even further. Ground-based spectroscopic surveys will improve the radial velocity measurements, providing better constraints on the star's three-dimensional motion, and theoretical advances in Oort cloud modeling, driven by the increasing power of computational facilities, will produce more detailed and realistic simulations of the encounter. All of these approaches, numerical simulation, analytic models, geological evidence, statistical analysis, the search for companions, and the study of tidal encounter synergies, converge on the same general conclusion. The Gliese 710 encounter will produce a significant perturbation of the Oort cloud. The resulting comet shower will increase the flux of long-period comets in the inner solar system for millions of years. The probability of a catastrophic impact on Earth during this shower is very low, but not zero, and the encounter, while the most dramatic in the near-term future, is part of a much larger pattern of stellar passages that has shaped the Oort cloud and the history of life on Earth for billions of years. Now we arrive at the part of this story that most accounts leave out. Not because it is secret, but because it is uncomfortable. It reframes the entire question, from a specific astronomical event to a fundamental truth about the nature of planetary systems, the fragility of life, and the illusion of cosmic safety. The deeper truth is this: the solar system is not a fortress. It is an open structure, embedded in a dynamic galaxy, subject to ongoing gravitational perturbations that have shaped its history and will continue to shape its future for as long as it exists. The Oort cloud is not a wall, it is a liability. It is a vast repository of potential impactors, loosely bound to the Sun, easily disturbed by the gravitational pull of passing stars, molecular clouds, and the galactic tide itself. And we have no way to monitor it, no way to survey it, and no way to protect ourselves from what it might send our way. Let that sink in. We have spent decades developing systems to track near-Earth asteroids, rocky bodies in the inner solar system whose orbits cross Earth's. As of the latest counts, astronomers have catalogued over 34,000 near-Earth objects, including more than 2,300 that are classified as potentially hazardous, meaning they are larger than 140 meters across and pass within 7.5 million kilometers of Earth's orbit. Programs like NASA's Planetary Defense Coordination Office, the Catalina Sky Survey, the Pan-STARRS project, and the European Space Agency's upcoming Near-Earth Object Mission Telescope are all dedicated to finding, tracking, and characterizing these objects. The goal is to provide years or decades of warning before a potential impact, giving humanity time to deflect the threat. And this system works for asteroids, for objects in the inner solar system, in well-characterized orbits, reflective enough to be detected by ground-based telescopes. NASA's DART mission, which successfully impacted the asteroid Dimorphos in September of 2022, demonstrated that kinetic impactor technology can change the orbit of a small asteroid. If we detect a threatening asteroid early enough, we may be able to push it out of the way. In January of 2025, the European Space Agency's Hera spacecraft arrived at the Dimorphos system to study the aftermath of the DART impact in detail, measuring the change in the asteroid's orbit, its mass, its internal structure, and the ejector pattern produced by the collision. The DART-Hera combination represents the first complete planetary defense test in human history, an impact followed by a detailed assessment. It is a remarkable achievement. But long-period comets from the Oort cloud are a fundamentally different challenge. They do not orbit in the inner solar system. They come from the outermost reaches of the Sun's gravitational domain, falling inward on hyperbolic or near-parabolic orbits that bring them past the planets at high speed. They are dark. Their surfaces are covered in ancient, radiation-darkened organic material, and they reflect very little light. They are invisible until they reach the inner solar system and begin outgassing, developing the characteristic coma and tail that make comets visible. By that point, they may be only months or a few years from Earth's orbit. The warning time for a long-period comet on an Earth-crossing trajectory could be as short as 6 months, possibly less. There is no catalogue of long-period comets because each one, by definition, has not been seen before. They appear without warning, pass through the inner solar system, and vanish back into the dark. Some return in millions of years, some never return at all. Consider the comet C2019Y4, also known as Atlas. Discovered in December of 2019, it was a long-period comet that brightened rapidly as it approached the Sun. For a time, it was expected to become one of the brightest comets in years. Then, in March and April of 2020, it broke apart. Its nucleus disintegrated into fragments, and it faded rapidly. Atlas was not on a collision course with Earth, but its rapid discovery and breakup illustrated a crucial point. We had only months of awareness before it passed through the inner solar system, and we had no ability to predict its behavior. A long-period comet on a collision course would present similar challenges: limited warning, unpredictable behavior, and no time to mount a meaningful response. This is not science fiction. This is the current state of planetary defense. We have no effective means of detecting or deflecting a large, long-period comet on a collision course with Earth. The kinetic impactor technology demonstrated by DART requires years of lead time. A nuclear standoff detonation, using a nuclear explosive to vaporize part of the comet's surface and push it off course, could work with less lead time, but has never been tested and faces enormous political and technical challenges. And even these options assume we detect the comet in time. Let that sink in. The most sophisticated planetary defense systems ever devised are designed to protect us from a class of objects that represents only part of the impact threat. The other part, long-period comets from the Oort cloud, is essentially undefended. Now consider the timescales. The Gliese 710 encounter will perturb the Oort cloud, injecting a pulse of long-period comets into the inner solar system. That pulse will arrive over a period of millions of years. During those millions of years, the background rate of long-period comets will be elevated, and the probability of a large impact on Earth will be correspondingly higher. Not dramatically higher, the probability of a large impact in any given year will still be measured in millions, but elevated nonetheless and sustained over a very long period. Over 1 million years, even a small annual probability adds up. If the probability of a catastrophic long-period comet impact in any given year is 1 in 10 million, then over 1 million years, the cumulative probability is roughly 10%. Over 10 million years, it approaches certainty. The individual annual risk is negligible. The cumulative risk over geological timescales is not. This is a concept that the human mind struggles to grasp. We are accustomed to thinking about risk in terms of individual events. Will this plane crash? Will this bridge collapse? Will this storm hit my city? These are risks with probabilities we can feel, probabilities that translate into immediate decisions. But the risk from Oort cloud perturbations operates on a completely different register. It is the risk of a slow accumulation. Each year, the risk is indistinguishable from zero. Each century still effectively zero. Each millennium still negligible, but each million years significant. Each 10 million years dominant. The danger is not any one comet. The danger is the steady, relentless statistical drizzle playing out across geological time. Consider an analogy. Imagine a game of Russian roulette with a revolver that has not 6 chambers but 10 million chambers. Each year, you spin the cylinder and pull the trigger. In any given year, you are almost certainly safe. You could play for a lifetime, for 100 lifetimes, and almost certainly never hear the click. But the game does not end. It continues for millions of years. And over millions of years, the cylinder finds its mark. The Oort cloud is the revolver. The galactic environment, the passing stars, the tidal forces, the molecular clouds, spins the cylinder. And the Gliese 710 encounter is the next spin. This is the tension at the heart of the story. On human timescales, years, decades, centuries, the threat from Gliese 710 is essentially zero. On geological timescales, millions of years, it is significant. And we are a species that thinks in human timescale but exists on geological ones. The deeper truth extends beyond Gliese 710. It extends to the very nature of the solar system's relationship with its galactic environment. The solar system is not isolated. It is part of the Milky Way, and it is subject to all the gravitational forces that operate within the galaxy. The galactic tide, the passages of molecular clouds, the encounters with other stars. These are not exceptional events. They are the normal operating conditions of a planetary system embedded in a galaxy. The Oort cloud is a natural consequence of planetary formation, and its perturbation by external forces is a natural consequence of galactic dynamics. Comet showers are not freak accidents. They are an expected feature of life in a galaxy. There is a tendency in popular science to present the solar system as a stable, orderly, and safe place. The planets orbit in neat ellipses. The sun shines steadily. The asteroid belt, despite its Hollywood reputation, is mostly empty space. The solar system has been stable for 4.6 billion years, and it will remain stable for billions more. This is true as far as it goes. The planetary orbits are remarkably stable. The sun is in the middle of its main sequence lifetime and will not undergo any dramatic changes for roughly 5 billion years. But stability in the planetary region does not mean safety from external threats. The Oort cloud is the soft underbelly of the solar system. It is the point of vulnerability, the place where the galaxy reaches in and rearranges our cosmic furniture. And Gliese 710 is the next hand that will reach in. Consider an analogy to terrestrial geography. An island fortress, surrounded by deep water, with strong walls and well-armed defenders, might seem impregnable. But if the island is surrounded by a vast field of floating mines that drift slowly, unpredictably, and invisibly beneath the surface, then the fortress is not safe at all. It is surrounded by danger that it cannot see and cannot control. The island is the inner solar system. The walls are Jupiter's gravity. The mines are the Oort cloud. And the currents that push the mines toward the island are the passing stars and the galactic tide. The analogy breaks down in one important respect. The mines, the comets, are not placed there by an enemy. They are a natural consequence of the process that built the fortress. The solar system created the Oort cloud as a byproduct of its own formation. The very process that assembled the planets scattered the leftover debris into a halo that now surrounds us, unstable and threatening. The danger is not external, it is structural. It is built into the architecture of planetary systems. It is, perhaps, unavoidable. There is a scaled comparison that may help convey the relationship between the planetary system and the Oort cloud. If the entire solar system, from the Sun to the outer edge of the Oort cloud, were shrunk to the size of a city, say, a circular area about 20 kilometers across, then the planetary system, from Mercury to Neptune, would occupy a circle roughly 2 meters in diameter at the center. The Kuiper belt would extend to about 3 meters, and the rest of the city, all 20 kilometers of it, would be the Oort cloud. The area that we think of as the solar system, with its planets and moons and asteroids, is a tiny island at the center of a vast, dark, vulnerable ocean. And somewhere out there, in the dark of the outer city, 64 blocks away and closing, is Gliese 710. The vulnerability of the Oort cloud raises a philosophical question that has no easy answer. Is it possible that every technological civilization in the galaxy faces this same threat? If Oort clouds are a natural byproduct of planetary formation, and theory suggests they should be, then every star with a planetary system probably has one, and every star, without exception, is subject to close encounters with other stars as it orbits the galaxy. This means that every planetary system in the galaxy is periodically bombarded by comets, dislodged from its own Oort cloud by passing stars. The galaxy is, in a sense, constantly firing at its own inhabitants. The rate of close encounters varies with the stellar environment. In dense star clusters, encounters are far more frequent than in the galactic field. In the core of a globular cluster, where stellar densities can reach 1 million stars per cubic parsec, close encounters happen so often that Oort clouds would be stripped away entirely within a few 100 million years. This may be one reason why globular clusters, despite containing millions of stars, are considered poor environments for the development of complex life. The cometary bombardment would be too intense, too frequent, too destructive. In the galactic field, where the Sun resides, stellar densities are much lower, roughly 0.1 stars per cubic parsec, and Oort clouds can survive for billions of years. But they are still perturbed, still leaking comets, still vulnerable to the occasional close passage. The galactic field is not safe, it is merely safer. And safer is a relative term when the timescales are measured in billions of years. Interestingly, the Sun's position in the galaxy may be somewhat fortuitous in this regard. The Sun orbits at a distance of about 26,000 light-years from the galactic center, in a region where the stellar density is moderate, neither too high, which would produce too many encounters, nor too low, which might indicate a region with too little chemical enrichment for rocky planets to form. This Goldilocks zone of stellar density has been proposed as one of the conditions necessary for the development of complex life, and it is sometimes called the galactic habitable zone. The Sun sits comfortably within it, but even within this zone, encounters happen. And when they do, the Oort cloud transmits their effects to the inner solar system with a delay of millions of years. This has implications for the search for extraterrestrial intelligence. The Fermi paradox, the question of why we have not yet detected signs of intelligent life elsewhere in the galaxy, given the vast number of habitable planets, has many proposed solutions. One of them is the Great Filter hypothesis, which suggests that some event or process reliably prevents technological civilizations from becoming long-lived. Could cometary bombardment be part of that filter? Could the regular disruption of Oort clouds by stellar encounters be a mechanism that periodically resets biological evolution on habitable planets, preventing any single lineage from developing technology? The evidence is inconclusive. The mass extinction that killed the dinosaurs was catastrophic, but it also cleared the way for the rise of mammals and, eventually, humans. Impacts can both destroy and create opportunity, but a sufficiently large impact, one caused by a body tens of kilometers across or larger, could sterilize a planet entirely, leaving no survivors and no second chances. If such impacts occur on timescales shorter than the time required for intelligent life to evolve, then the Oort cloud becomes a cosmic trap, a feature of planetary systems that ensures they never produce lasting civilizations. Consider what the history of life on Earth would look like if the Chicxulub impact had been slightly larger, a body 20 kilometers across instead of 10, or 50, or 100. The Chicxulub impact killed the dinosaurs, but left the mammals alive to inherit the Earth. A larger impact might have killed everything larger than a bacterium. Life might have had to start the climb toward complexity all over again, from single-celled organisms. That climb took roughly 3 billion years the first time. There is no guarantee it would succeed a second time, or a third, or a 10th. The window for intelligent life to evolve might be constantly closing, reset by each major impact, never staying open long enough for technology to emerge. On the other hand, moderate-sized impacts may be necessary for biological diversity. The Chicxulub extinction cleared ecological niches that had been dominated by dinosaurs for 170 million years. Without that clearing, mammals might never have diversified, primates might never have evolved, intelligence might never have emerged. In a strange and troubling way, we owe our existence to a catastrophic impact caused by an object that may have originated in the Oort cloud. The very mechanism that threatens us is also the mechanism that made us possible. This paradox, that cosmic bombardment is both a threat to complex life and a prerequisite for it, is one of the deepest ironies in the story of life on Earth. The Oort cloud giveth, and the Oort cloud taketh away. There is one more dimension to this deeper truth that deserves consideration, and it involves time in a way that the human mind finds particularly difficult to process. The effects of the Gliese 710 encounter will not be felt for millions of years. The comet shower will begin roughly 2 million years after the closest approach, and will persist for perhaps another 3 million years after that. The total duration of the elevated cometary flux could span 5 million years or more. Human civilization, at roughly 10,000 years old, occupies less than 1/500th of that timescale. To put it differently, if the Gliese 710 comet shower were a single day, all of recorded human history would occupy less than 3 seconds of that day. We cannot plan for events on these timescales. We cannot prepare for them in any meaningful way. Our institutions, our governments, our civilizations rise and fall in centuries or millennia. The comet shower will outlast them all. If there is a lesson here, it is this: the universe operates on timescales that render all human planning irrelevant. The threat from Gliese 710 is real, but it is not our threat. It belongs to whatever comes after us. Whatever species, whatever civilization, whatever form of life exists on Earth 3 million years from now. And if the history of life on Earth is any guide, what comes after us will be as different from us as we are from the creatures that lived 3 million years ago. 3 million years ago, the genus Homo had barely emerged. Australopithecus still walked the savannas of East Africa. The stone tools of our ancestors were crude. Language, as we understand it, may not yet have existed. In 3 million years, the distance between then and now has been traversed by evolution, producing a species capable of building particle accelerators, launching satellites, and predicting the trajectories of stars millions of years into the future. What will 3 million more years of evolution produce? We cannot know. But whatever it produces will face the cometary legacy of Gliese 710, whether it understands the threat or not. This is speculative, of course. We have only one example of a technological civilization, our own, and drawing general conclusions from a sample of one is always dangerous. But it is worth noting that the Oort cloud, for all its scientific fascination, is fundamentally a threat multiplier. It converts the gentle, ongoing process of stellar encounters into a mechanism for planetary-scale destruction. And Gliese 710 is the next trigger in a process that has been running for billions of years. Where does all of this leave us? Not as astronomers or physicists, but as human beings, as temporary residents of a small rocky planet orbiting an ordinary star, floating through a galaxy full of other stars, all of them in motion, some of them heading our way. The first implication is practical. We need better surveys. The current planetary defense infrastructure is focused almost entirely on near-Earth asteroids, objects that are close, bright, and in well-characterized orbits. This is important work, and it has produced real results. But it leaves a critical gap in our defenses. Long-period comets, arriving from the Oort cloud on orbits we have never seen before, represent an unmonitored and essentially unpredictable threat. We need dedicated surveys capable of detecting incoming comets at the greatest possible distance, providing the maximum possible warning time. The Vera C. Rubin Observatory, currently under construction in Chile and expected to begin operations in the mid-2020s, will be a significant step forward. Its 8.4-meter mirror and wide field camera will survey the entire visible sky every few nights, and it is expected to discover thousands of new comets and asteroids. But even the Rubin Observatory cannot see into the Oort cloud. The only way to detect an incoming long-period comet is to wait until it reaches the inner solar system and begins to outgas and brighten. There have been proposals for space-based surveys that could detect incoming comets at greater distances. An infrared telescope stationed near the Sun, looking outward, could detect the faint thermal radiation of an incoming comet before it begins to outgas. The NEO Surveyor mission, a NASA infrared space telescope scheduled for launch in the mid-2020s, will primarily target near-Earth asteroids, but will also detect some long-period comets. However, no existing or planned survey is optimized for the detection of large, dark, slow-moving objects in the outer solar system. The Oort cloud remains, and will remain for the foreseeable future, a blind spot in our awareness. The third implication is about technology and preparation. Even if we cannot prevent the Gliese 710 encounter or the comet shower that follows, we can prepare. We can develop more capable deflection technologies. We can establish monitoring systems designed specifically for long-period comets. We can study the Oort cloud through indirect methods, modeling the orbits of observed long-period comets to constrain the density and distribution of the cloud. We can also continue to refine our understanding of the Gliese 710 trajectory, using future Gaia data releases and ground-based spectroscopic observations to narrow the uncertainty in the closest approach distance and timing. The second implication is scientific. The Gliese 710 encounter, while it cannot be prevented or altered, can be studied. In 1.3 million years, when the star arrives, it will provide an unprecedented opportunity to observe a stellar flyby in real time, assuming, of course, that someone is here to observe it. The perturbation of the Oort cloud will produce observable effects, an increase in the rate of long-period comets entering the inner solar system, changes in the distribution of cometary orbits, and possibly even the disruption of objects in the outer Kuiper belt. These observations would provide the first direct test of the theoretical models that have been developed to predict the effects of stellar encounters. But perhaps the most important implication is philosophical. The story of Gliese 710 is at its heart a story about time. Human civilization is roughly 10,000 years old. The agricultural revolution began about 12,000 years ago. Written history extends back about 5,000 years. The entire arc of human civilization, from the first cities to the present day, would be a rounding error in the timeline of the Gliese 710 encounter. 1.3 million years. That is the lead time. And the comet shower that follows will last for another 2 to 4 million years after that. The total duration of the event, from the star's arrival to the end of the elevated cometary flux, is roughly 3 to 5 million years. Our species, Homo sapiens, has existed for approximately 300,000 years. The entire existence of our species, from the first anatomically modern humans to the present day, would fit inside the duration of the comet shower multiple times over. We are not equipped to think about time on these scales. Our brains evolved to plan for the next meal, the next season, the next generation. We can, with effort, imagine decades. We can, with great effort, imagine centuries. But millions of years? That is not a human timescale. It is a geological timescale, a biological timescale, an astronomical timescale. It is the timescale on which mountains rise and fall, on which species evolve and go extinct, on which continents drift and oceans open and close. And it is the timescale on which the Gliese 710 encounter will play out. This mismatch between human perception and cosmic reality is not unique to the Gliese 710 story. It pervades all of astronomy. The light we see from the nearest star left 4 years ago, the light from the nearest galaxy left 2.5 million years ago, the cosmic microwave background left 13.8 billion years ago. The universe operates on timescales that make human life look like a flash of lightning. Bright, brief, and gone. We live in a thin slice of now. Our memories extend back a few decades. Our records extend back a few millennia. Our geological knowledge extends back a few billion years. But the future, the deep future, the future on which the Gliese 710 story plays out, is a country we can see from a distance but never visit. We can calculate what will happen there. We can model it, simulate it, predict it with impressive precision. But we cannot experience it. And this gap between what we can predict and what we can experience is the defining feature of our relationship with the cosmos. We are creatures of the moment, gifted with the ability to understand eternity, but trapped in a life that spans at most a single century. And yet we are here. We are the ones asking the questions. We are the ones building the telescopes and running the simulations and calculating the trajectories. For the briefest of moments, on the scale of cosmic time, a species exists on this planet that is capable of knowing about Gliese 710, of predicting its approach, of understanding its implications. That is not nothing. That is extraordinary. In 4.6 billion years of solar system history, no one has been here to watch the stars go by. Now, for a few thousand years, a cosmically insignificant interval, someone is watching. And what we see, when we watch carefully enough, is that the universe is not hostile, it is not malevolent, but it is not safe either. It is indifferent, and indifference, on cosmic scales, can be as dangerous as any intentional threat. The galaxy does not know we are here. The stars do not aim for us. Gliese 710 is not coming because we did something wrong or because we are in the wrong place. It is coming because it is on its orbit, following the laws of gravity, moving through the galaxy as it has moved for billions of years. It will pass through our neighborhood the way a car passes through an intersection. without noticing, without caring, without any awareness of the pedestrians on the sidewalk and the debris it kicks up. The comets it sends tumbling toward the inner solar system will fall where they fall, regardless of whether anyone is there to be struck. This is the nature of the cosmos. It is not designed for us. It is not designed against us. It is not designed at all. It simply is. And the challenge of being a conscious species in an unconscious universe is learning to live with that knowledge, to take the threat seriously without being paralyzed by it, to prepare where preparation is possible, and to accept, with grace and without despair, the risks that cannot be mitigated. There is a final implication that touches on something even more fundamental. The story of Gliese 710 challenges a deeply held assumption that runs through much of human thought, the assumption of permanence. We build monuments to last for centuries. We write constitutions to endure for millennia. We plant trees that will outlive us. We imagine our civilizations extending into the indefinite future, growing and spreading and persisting. And all of this rests on an unstated assumption that the Earth will remain habitable, that the solar system will remain stable, that the cosmic environment will remain benign. The Gliese 710 encounter reminds us that this assumption has limits. The Earth has been habitable for roughly 4 billion years, and it will likely remain habitable for another billion years or so, before the sun brightens enough to boil the oceans. But habitable does not mean safe. The Earth has experienced 5 major mass extinctions in the past 540 million years, each one caused by a combination of factors that included, in at least some cases, impacts from space. The history of life on Earth is not a smooth upward curve. It is a jagged line, punctuated by catastrophic drops, each one followed by a slow, painful recovery. The comet shower from Gliese 710 will add another potential punctuation mark to that jagged line. Not an inevitable one, not a certain one, but a possible one. And the fact that we can see it coming, however dimly, however uncertainly, is itself a kind of gift. It is information. It is knowledge. And knowledge, even knowledge of danger, is better than ignorance. The ancient Greeks told a myth about Cassandra, a prophetess cursed to see the future but never be believed. Modern astronomy is the opposite of Cassandra. It sees the future and is believed. The data is there. The calculations are sound. The trajectory is confirmed by the most precise astrometric instruments ever built. The star is coming. What we do with that knowledge, whether we use it to improve our planetary defense, to deepen our understanding of the solar system, or simply to marvel at the immense, intricate, terrifying machinery of the cosmos, is up to us. The knowledge itself is a gift, and it is a gift that no previous generation of human beings has ever possessed. We began with a fact. A star is heading toward our solar system. Its name is Gliese 710. It is 64 light-years away and closing, in approximately 1.3 million years. It will pass through the Oort cloud at a distance of roughly 10,000 astronomical units from the Sun, closer than any predicted stellar encounter in the next several million years. We have traced the discovery of this trajectory, from the early measurements of the Hipparcos satellite to the revolutionary precision of the Gaia mission. We have explored the structure of the Oort cloud, that vast and invisible reservoir of trillions of icy bodies that surrounds the Sun at distances far beyond the planets. We have examined the physics of gravitational perturbation, the mechanics of comet showers, and the simulations that predict a significant increase in the rate of long-period comets entering the inner solar system in the millions of years following the encounter. We have looked at past stellar encounters, Schultz's star, which grazed the outer Oort cloud 70,000 years ago, and at the broader statistical picture, a galaxy in which close stellar passages are not rare events but routine occurrences, happening dozens of times per million years at varying distances. We have explored the link between Oort cloud perturbations and mass extinction events, including the possibility that the Chicxulub impactor itself may have been a long-period comet fragment sent sunward by a distant gravitational nudge. And we have confronted the deeper truth. The solar system is not a sealed fortress. It is an open structure with a vast, vulnerable halo of icy debris that extends 100,000 astronomical units from the Sun. That halo is constantly being stirred by the gravitational forces of the galaxy. The tides, the molecular clouds, the passing stars. Our planetary neighborhood, the small disk of planets and asteroids that we think of as home, sits at the center of a much larger, much more hazardous space. The planets will be unaffected by Gliese 710's passage. The star will not come close enough to perturb their orbits or disrupt the gravitational architecture of the inner solar system. Earth will not be scorched. The moon will not be ripped away. The tides will not change. From the standpoint of the planets, the encounter will be a non-event. But this is precisely what makes the story so unsettling. The danger does not come from the star itself. It comes from what the star does to the periphery, to the vast, invisible, uncharted outskirts of the solar system that we cannot see, cannot reach, and cannot defend. The threat is indirect. The threat is delayed. The threat is statistical. And it is precisely this indirectness that makes it so difficult to take seriously and so dangerous to ignore. The history of life on Earth has been shaped by events from the outer solar system. The water in your glass may have been delivered by comets during the early bombardment of the Earth. The extinction of the dinosaurs may have been caused by a comet perturbed from the Oort cloud. The rise of mammals, and eventually humans, may have been made possible by that same comet. We are, in a sense, products of the Oort cloud's instability, children of cosmic chance. But from the standpoint of the Oort cloud, it will be a seismic shift. Billions of cometary orbits will be altered, millions of objects will be redistributed, and a fraction of them, a small but non-zero fraction, will be sent tumbling inward, toward the sun, toward the planets, toward us. Will any of those comets strike the Earth? The probability is low, extraordinarily low. The vast majority of long-period comets that enter the inner solar system pass harmlessly through, swinging around the sun and returning to the outer dark. The probability that any single comet will hit any single planet is measured in billionths. But the elevated cometary flux will persist for millions of years, and over millions of years, small probabilities accumulate. The Earth will continue to orbit the sun. The moon will continue to orbit the Earth. The seasons will continue to turn. Life will continue to adapt, to evolve, to fill every available niche. And somewhere in the outer darkness, comets perturbed by Gliese 710 will be falling silently inward, each on its own trajectory, each governed by the same laws of gravity that hold the planets in their orbits. Most will miss. Most will swing around the sun and return to the cold. But the process is relentless, and the timescale is vast, and the universe does not negotiate with probability. We will not be here to see it. 1.3 million years is too far away for any prediction about human civilization to be meaningful. We may be extinct. We may have colonized other star systems. We may have evolved into something that no longer resembles what we are today. The encounter with Gliese 710 will play out regardless, on its own timeline, indifferent to the presence or absence of observers. But the fact that we know it is coming, that we can predict it, model it, and prepare for its implications, says something profound about what we are. We are a species that has learned to read the motions of stars. We are a species that has built instruments capable of measuring the velocities of distant suns to within a few meters per second. We are a species that can project the trajectories of celestial objects millions of years into the future. In the entire 4.6 billion year history of the solar system, this has never happened before. No organism has ever known what was coming. No consciousness has ever looked ahead and seen the shape of the future, however dimly. We see it now, a dim orange star, invisible to the naked eye, drifting through the constellation Serpens, moving toward us at 14 kilometers per second. Ordinary in every way except its direction. It will take more than 1 million years to arrive. But it is on its way, and as it approaches, decade by decade, century by century, millennium by millennium, it will grow imperceptibly brighter. Not enough for any human eye to notice over a single lifetime, but over the millennia, it will climb the magnitude scale, rising from an invisible speck to a faint telescopic point, from a faint point to a naked eye star, from a naked eye star to a prominent fixture in the night sky. If anyone is here to watch, they will see a new star growing brighter in Serpens, a star that was not bright enough to notice 1 million years earlier, and they will know. If they have inherited our knowledge, if they have kept our records, if they have maintained our understanding of celestial mechanics, that this star is not merely passing through, it is reaching into the outermost edges of their solar system and reshuffling the cometary orbits that have been stable since before their species existed. The night sky looks peaceful. The stars appear fixed. The universe seems stable and silent, but appearances deceive. The stars are moving, the galaxy is churning, and every now and then, on timescales that make human life look like the blink of an eye, a star wanders close enough to reach into the outermost edges of our solar system and rearrange what it finds there. We are made of the same material as the comets in the Oort cloud. The water in our bodies, the carbon in our cells, the iron in our blood, all of it was forged in the same stellar furnaces, expelled by the same supernovae, condensed from the same solar nebula. The comets that sit in frozen silence at the edge of the solar system are our distant cousins, formed from the same primordial cloud, separated by 4.6 billion years of gravitational sorting. When Gliese 710 passes through and sends some of them falling sunward, it will be sending pieces of our own origin story back toward us. Fragments of the cloud from which we were born, returning home after billions of years in the dark. There is something poetic in that, and something terrifying. The same material that gave rise to life could, if it arrives in the wrong form at the wrong time, extinguish it. Gliese 710 is the next one. It is coming, and the universe, as always, does not wait.